Hello, hello, hello. Let me turn down the music a second. Yes. So how do we do CH3, CH2, CH, CH, OH? And the OH is in parentheses. Typically, this is tricky in my this is a little bit, I guess, past what we're or I would say it's a little bit in line with maybe class 19. Well, it is kind of class 18 a little bit, but not even really. It isn't really class 18, but the way I would envision it is I need to make sure carbon has 4 bonds to it, whether those 4 bonds are single bonds, and so this CH3 is likely the terminal CH3. So when I'm reading this formula, the CH3 is probably a terminal atom, and then it goes to a CH2. Let me share my screen a second. Open up a ChemDraw. Close that, close that, close that. Okay. Okay. So I'm kind of seeing the CH3, and let me zoom in a little bit. Okay, great. So C. So I see CH3, and typically, this isn't always the case, but when I see a list where all the carbons aren't grouped, where it isn't like C6, H8, O1, if they give it to me in a list where it's carbon, then hydrogen, carbon, then hydrogen, carbon, then hydrogen, they're likely listing the carbon chain, and then I need to decide where are there double bonds or possibly triple bonds to make up for carbons that don't have 8 bonds. So this CH3, I've got 3 bonds to it, to the 3 H's, and then it's likely going to the next carbon. So the CH2, so there's a C. Now I have 4 bonds to that first carbon in this chain, or in this this selection you've given me. And then that is an H2, they're telling me. And so it's like, okay, that CH2 has 1 bond back to the CH3 carbon that came first. Then I have a CH2. Then it says I go to a CH. And so if this is connecting to just a CH, and let me kind of fix this so it lets me do some, because ChemDraw doesn't like it when we put in weird atoms, but it tells me it goes to a CH, and then I'm kind of feeling that once again, when it brings another CH, it's going out to another CH. So I'll add another CH. Tell ChemDraw, I know I'm writing it wrong for now, but I'll fix it later. CH. Don't interpret chemically. Let's just change that to another. So I think the short answer is that I'm probably going to try to align all the C's one after the other. And then this, so it's CH3, check, in red. Boom. That's the first part of it, and then it goes to a CH2 is kind of the next way I read it. And then it goes to a CH followed by another CH. And then it goes to an OH in parentheses, which is the one thing I'm a little bit maybe unsure about, but for now I'm just going to put an OH at the end. And let me even expand this out a little bit. And the OH is, or oxygens in general, when I think about how the periodic table goes boron, carbon, nitrogen, oxygen, fluorine, typically this is for me, I do sometimes just forget about boron only because it's typically only 3 bonds to boron, but sometimes more. It's one of the weirder ones, but I am always thinking, let me bring this up a little bit. So this is kind of a little side point of something that I look at pretty consistently. And this isn't, you have to be careful because this isn't always the case, but this is something this is a pattern that is pretty easy for me to use to explain how I'm making some decisions here. But carbon typically has, ChemDraw's like, what are you doing? Do not interpret chemically, please. And so for carbon, this is typically 4 bonds, 0 lone pairs. is typically what carbon does. And then when we go to, this is just so awkward. Let's space these out a little bit. And bring it down a little bit in size. So carbon usually is 4 bonds, 0 lone pairs. Nitrogen is typically, not always, but typically 3 bonds, 1 lone pair. And what I'm noticing about here in oxygen is typically I see 2 bonds, 2 lone pairs. And so right now when they're saying this CH then has a parenthesis OH coming off at the very end, I'm already seeing that it looks like that oxygen is happy. It has 2 bonds, 1 to an H, 1 to the last C in the thing, and 2 lone pairs. And so I'm thinking oxygen's good. Hydrogens, all my hydrogens need to have at least 1 bond. Of course they do. Last but not least, do all my carbons have 4 bonds? Red, check. 3 to hydrogen, 1 to a carbon. Blue carbon, check. 1 to the green carbon, 1 to the red carbon, good. But here, it's what's, this has to, or I'm going to say, to guess what this structure is, this Lewis structure. I'm copying a bunch of them. My best guess for this Lewis structure is that I don't see any indication of any special connections that I'm missing. And to make the octet work, I need to fix these 2 carbons. I can't put a double bond here because now the blue has not 4 bonds to carbon, but now 5, so I can't do that. I can't do it on this side because now oxygen has 3 bonds to it, and so formal charge gets weird here. But I think it's telling us there's a double bond in this molecule. And cool thing with ChemDraw is you do Control-Shift-K, and it'll clean it up. So I'm holding down Control-Shift-K, and it kind of, well, it does one. It adjusts the geometry a little bit. It didn't, but I'm sorry. I stopped it from interpreting it chemically, so it did it not well. So let's see if we can say, get back to interpreting chemically. Okay, that one's right. Go back to interpreting chemically. Interpret. Now let's see if it does a little bit better job. This is its best attempt. It doesn't like bringing the lone pairs with it. But even this I'm not crazy about in terms of the final step we're trying to take is, yes, this is the right Lewis structure. I'm fine with the Lewis structure. But taking it to Vesper is to saying that this red carbon is sp3 hybridized, has 4 areas of electron density. It doesn't have a lone pair next to a double bond, so it should be as it is. So what I'm going to do is actually wedge one of these and dash the other. And this is going beyond your question, but I'm just saying this is kind of how this is pretty good. But now I want to say, okay, well, what about the blue carbon? Blue carbon is next to a double bond, so I want to be careful about its hybridization, but it doesn't have a lone pair, so it shouldn't be weird. So again, I need to put in a wedge and a dash to say this is sp3. This is using px, py, pz. There should be 3-dimensionality to this carbon that I should indicate with my hydrogens, and so I put those on a dash and a wedge, leave 2 in the plane. And typically, organic chemists love to do skeleton structures where we walk a skeleton like this, where we put all of our in the plane bonds kind of going up and down on this. I'm doing a horrible job, but even if I just click on ChemDraw, it approximates kind of what, well, not actually it doesn't, but it's, if I force it to, a lot of us like to write in this very px, py, pz oriented thing, and so even ChemDraw does it. But anyways, let's get back to what I'm trying to say. But so the red and the blue are both sp3, and I have no doubts about it. The green and the teal, because I saw that those carbons didn't have their octet complete based on the Lewis, kind of what you were giving me, but this molecule, I'm likely being asked to make one that is filling the octet for all of the molecules, and so that's why I put a double bond there between those 2 molecules, which then tells me that these are 3 areas of electron density, so the green and the teal carbons are sp2, and if they're sp2, there are different ways I can show sp2 molecules, but as I've written it on the page, I need to keep it in one plane. So sp2 molecules, so green and teal, are sp2 molecules. And again, remind yourself what's so important in my opinion is that when we say sp3, we are saying there is X there is Y, and there is Z. Your part of your structure should then indicate things that are Z, things that are Z, things that are Y, and things that are X. These are all, I'm seeing all Y, X, and Z on blue and on the blue and the red carbon. But if the green and the teal, if I only choose two P's, if I only choose the PX and the PY, then I can't leave the screen, because the screen is the XY plane. What you're looking at is the XY plane. We're envisioning these wedges and dashes coming out and going into the screen. And so all of these bonds coming off of the green carbon and this carbon, you're going to notice there is no wedge, there is no dash. This is using Y and X, this is using just Y, Y and X, just Y, Y and X. And yes, that is an oversimplification, but we can know that if it's not a wedge or a dash, I needed X or Y. If there is a wedge or a dash, there must be PZ involved. But anyways, I'm taking your question a little bit further. And then one thing to note, the kind of keep an eye out, is this is the got you on what we were kind of saying. We want to, in every time we look at a structure, see the C-double-O bond and highlight this in your head. Say, this is something that when I see this in a structure, I'm going to go one atom away and I'm going to see if it has a lone pair. Oxygen has two lone pairs. And so if I'm asked to say what is this bond angle based on egg, based on just simply following patterns, I'd say I'd expect it to be a little bit less than 109.5. Has four things of electron density, but two are lone pair, so it's going to shrink the 109.5 a little bit as the electrons repulse each other more because they're not tied to an atom. So I'd say probably less than 109.4. But if someone told me this bond is actually closer to like 120, maybe 117, then I'd make the argument that this oxygen is actually sp2 hybridized. Is that the case for this molecule? I doubt it. It typically is going to be for amides. The C-double-O to an N is where we most see it. But if we tell you the data says it and you have to defend it, then I wouldn't call this sp3. I'd say, well, it's sp2 because it's next to a double bond. But we would need data to make that decision. Or if we're asked to talk about its egg, I would name its egg by naming the amount of areas of electron density, but then comment on, however, it is next to a pi system. So those pi systems might impact that these electrons may choose to be in a p orbital, stabilizing them. So anyways, does that help a little bit? It is quote unquote a little bit beyond where we're going, but I'm wondering to myself, do we ever spend a whole day on organic structures that are linear where you have to create it? No, it feels like we mostly go into talking about, we're going to show you more complex Lewis structures and then ask you to consider how are these isomers of one another, how you can give me the same chemical formula and I can generate multiple answers to spatially how I can make that molecule. And then we have to ask what is different about those spatial representations that I showed you. So don't worry about that, but I hope that helps a little bit. Awesome. is so bad. Oh my gosh. Oh, I did not write that well. All right, guys, I'm going to call that for now.